Ladies and gentlemen, my name is François Breton. I am a PhD in organic chemistry and specialist of the hard coating process. So that's why today I will demystify for you the deep coating process for hard coating your lenses. So first of all, let's have a look at the typical design of a deep coating machine. We must assume that first of all, the lenses that will get inside this machine, they are apparently clean, so that you don't see any dirtiness at the surface. So you see here a typical sequence of tanks where you have ultrasonics in some of them, and some of other tanks do not have ultrasonics. So you end up here. You have an infrared oven for drying the lenses after the final rinse. These tanks, are filled with some liquids that I will describe later, and you have some rinsing with tap water and DI water. What you're expecting at the exit of this machine, on the right-hand side, you have the coating tanks and the infrared drying tank. That your lenses should have good quality for cosmetics, thickness, and adhesion of the hard coating. But actually, this machine is not responding to this ideal design of activation with ultrasonics. Because what we need here is no more than 5 tanks before drying. It could be even reduced to 3 tanks if you don't have the space or the budget or enough quantity of lenses to take into account. Because basically, what is happening between tank 1 and tank 3 is really similar. This is just activation with a strong alkaline subspecies, which is in this case KOH or potassium hydroxide, which would not work alone without the help of some surfactants. Of course, you need temperature. That is the engine of the chemical reaction that is taking place, and ultrasonics, so that you can not only react the surface but also inside the lens, and this is what we know the best possible way to achieve adhesion, which we'll see a bit later why. So the tap water that goes in tank 2 and tank 4 is actually taking care of rinsing the surfactants. Those surfactants, they will not be removed completely if only using tap water without ultrasonics and tap water without heating, which is the case in the machine that you saw before. So when you have the possibility of having 5 tanks and not 3, you will repeat in tanks 3 and 4 what you see in tanks 1 and 2, except that the concentration in tank 3 will be lower than in tank 1 in order to make the rinsing easier, while increasing further the activity of the surface of the lens. And finally, in tank 5, the DI water, which role is to remove the ions from the tap water. So here we have to limit the temperature to 40 degrees, because otherwise the resins that are used to generate the DI water will be ruined faster, and then you will not be able to keep the performance of your rinsing for too long. So To summarize this, we should say that the surfactants must have also the capability of chelating any impurity. That's why we select the gluconate or some phosphonates. Could be from sodium or from potassium. The activation time depends on lens materials. As you probably know, the higher the refractive index, the longer the activation time must be. Typically, it can go up to 20 minutes for the 174, which is a very difficult substrate to tackle. What else? Yes, the city water must have conductivity between 250 and 400 microsiemens per centimeter, because when it's lower than that, then you don't have enough ionic strength to remove with efficiency the surfactants. And when it is higher than that, then it may be difficult to remove all the ions without damaging the resins of the DI water. Bear in mind also that the flow rate for the tap water should be adjusted so that you can remove all the water, change all the water during the process interval time, and so that you don't have to take care too much of the surfactant that you use. And finally, the DI water conductivity must be less than 0.3 microsiemens per centimeter, because otherwise you will see some white dots appearing, those white dots being made of calcium carbonate, because you have high alkalinity at the surface of the lens. And if you have in your DI water some calcium, magnesium ions, this will create the carbonates that you will see. So lots of things are appearing in the machine, happening in the machine, and what we are interested is the adhesion phenomenon. How does it happen? Here you see the structure of the 1.5 monomer, which of course is repeated lots of times to make the lens. So the alkaline species we describe here, with the potassium hydroxide, is actually reacting on the C double bond O, which is also called carbonyl group. This carbonyl group will create some enolates, where you have a lot of electrons around the oxygen atoms, and this will generate the site that is needed to bond the lacquer through its epoxy group, which is present already in the formula of the lacquer. And as you could see here, you achieve some chemical bonding between the substrate and the lacquer, so that you can be sure that you have extremely strong adhesion that will survive all the further steps and all the life of the lens. But what is deep coating actually? Well, deep coating is it's made out of 3 steps. The first step, of course, is imagine you dip the lens inside the lacquer. So at this stage, nothing happens, just that you create some turbulence in the liquid that you must wait a little bit to set up. Then, what is happening is really when you lift out the lens from the tank, then you see appearing on the lens a wet layer, which is the liquid flowing alongside the lens and getting back inside the liquid. And as soon as the lens is completely out of the liquid, then you have at the same time evaporation of the solvent and dripping of the excess liquid inside the tank, which this could be explained very adequately with Landau-Levitch equation. Because what is important for you is the thickness of the coating that you apply that way. And you can control, because you have control about the speed, of course, and the viscosity of the lacquer by playing with the solvent ratio. But mostly you see that this coating thickness is linked to lift out speed, which will tell you that the higher the speed, the higher the thickness. So what is deep coating also? I can say that there are this an addition of a lot of phenomena occurring at the same time. As you could see here, typically on this drawing, you have at the same time the gelation that is appearing because the solvent is evaporating. So all the salts, it means since the chemical species inside the lacquer are able to react between each other, taking into account that the viscosity would become much higher than it used to be before the evaporation of the solvent. So in the end, we must say that, of course, we have lots of different substrates, not only differing from the refractive index, but also from the manufacturer. And so this must include that we have lots of different processes for optimizing the yields. And in order to have all those processes, you need to have, of course, some flexibility of the machinery that you are using. This flexibility of machinery requires, of course, the same your mental flexibility. But don't worry, of course, this is linked to chemistry and physics, as you could see in my previous slides. But no, it's not so difficult to master. It's just a matter of understanding physics and chemistry. And I'm sure that this will lead to a lot of questions from your side, ladies and gentlemen. So I will be pleased to answer them when you want.
Yeah, first of all, Francois, I would like to thank you for your very interesting and important contribution to the theoretical understanding of dip coating. For me, as a physicist, on the one hand, the process looks almost too complicated to be fully represented by a model. On the other hand, the dip coating process has been used in practice for a very long time and is probably completely optimized. And that leads me to my first question. Where exactly can the process be improved through your theoretical knowledge? What does the typical lab look like that you can help?
Well, as I mentioned in my document, my paper, most of the time, the machine manufacturers, they did not know too much about chemistry, and or their main interest was to sell more consumables. And given the fact that their customers did not know anything at all about chemistry, but maybe H2 plus O2 makes H2O, okay, that's from the childhood that they might remember that. They could easily bullshit their customers and use this to their advantage. So, and nobody was interested in getting to behind the lines to explain what is everything, because the interest when you have customers that are not knowledgeable, you can tell them what you want, they will believe, and they will be scared to change to another supplier, of course, because we don't know what's going to happen. Wow, if we change anything. So better we have a process that is running smooth for us. So let's keep it, because we never know what's going to happen.
Mm-hmm. Mm-hmm. Okay. um, at the beginning of your presentation, you said, or you assumed that the lens is apparently clean.
Yeah.
That's not exactly a scientific description of the properties of the lens surface. So does the cleaning process not belong to the dip coating process? That's what I.
Well, actually, yeah, because the thing is, for the user, the lens manufacturer, he will probably have to remove the dust and the marks for the progressives that are still visible. which you will do most of the time manually with acetone or isopropanol if it's polycarbonate. So the lens look okay, but in the deep coating process, what we see is not cleaning at all. It is just activation process, and that's where there is the big difference with the process that people believe that is a cleaning rinsing process, and that's why the rinsing with acidic material is a nonsense when you think that it is an activation process. If it's a cleaning rinsing process, yes, but it has to be solved very differently.
Mhm. And I have another question regarding the tap water. As far as I know, tap water can be very different all over the world, all over the day, all over the week. So you said that it's important to have the conductivity in a certain range. And of course, the temperature must be 50 or something like that degrees. But
Yeah.
is there anything else we have to look at when regarding tap water?
Of course, it's normally comes to the equipment after some filtration, and especially iron is very detrimental. So, but most of the time the machines are equipped with filters for getting this water in.
Mhm.
What they are not equipped with is heating and ultrasonics, apart from some equipment manufacturers. But I don't want to make some publicity for them. Just the ones who do that are right.
Mhm. Okay. Um, Regarding the lacquer, I have seen some lenses where interferences do occur because the lacquer does not have the same refractive index
Yes.
as the material. And from a chemical point of view, is that a difficult thing to adapt the lacquer index to the material? And is it more difficult to have a high refractive index than a lower refractive index?
Absolutely, it is. It is. Well, more or less, the basic matrix for the lacquer is polysiloxane, which is in order to mimic silica, or to give a surface that is similar to mineral glass. But it's a 1.5 index. This, and if you want to go higher index, what do you have to do? You have to incorporate certain nanoparticles, mostly based on TiO2 or ZrO2, titanium oxide or zirconium oxide, that will raise the refractive index. However, when you do that, you have a problem of stability and transparency. These nanoparticles, especially if you think about TiO2 is really sensitive to UV. It's by itself linked to photocatalysis. So if you can make a high index lacquer that will be cheap to make, but it will not last very long because the interaction with UV. So in order to prevent this UV interaction, these nanoparticles must be protected with in a core shell structure, so that the UV light does not react with the TiO2. However, this is making so a bit difficult to incorporate finally in the matrix of the lacquer, and also it is distorting the structure of the lacquer. So you have a lacquer that is from a viewpoint of optics quite good. It means no Newton rings. But on the other hand, the mechanical properties are really going down, simply because you start from a very homogeneous network and you distort it. So you can imagine the effect on the from a mechanical viewpoint. That's what it is. And so there's very few actually nanoparticle manufacturers that are offering that to the optical industry. There's only one in Japan, and it's taking advantage of its it's got all the market to put the price very high. Therefore, high index lacquers are much more expensive than low index. And the only difference that the only advantage that they bring compared to low index is that you don't see Newton rings. However, from the mechanical properties, as I said, they offer lower mechanical properties.
Okay. That brings me to another question. You presented us the Landau-Lewitsch equation when dipping the lens into the fluid or into the lacquer and extracting it, and this equation gives us, as far as I understood, the thickness of the lacquer on the lens. And
yes.
In theory, the thickness should be the same all over the lens, but there are turbulences, and
Absolutely.
we have bifocals with certain how do you say
you see sometimes a teardrop on the bifocals. Yes.
Yeah, for example.
Yeah.
For example, and what does your theory say about this? Is there any new idea how to avoid these problems?
Of
or
course,
to overcome?
that it cannot be fully overcome, but there are ways to overcome the problem. When talking about the homogeneous thickness from top to bottom, it's actually linked to the fact that we don't have really a Newtonian type of liquid. Because it's not an homogeneous liquid, it contains a lot of different chemicals inside, so that's why it's not really Newtonian. Therefore, it's highly linked to the gravity, the fact that you have some flow along the lens, and if you keep the same speed all along the lift out, then you will get this gradient of thickness. If you can reduce the speed during the lift out, some robots can do it, then you can get homogeneous thickness. But okay, most of the machines that in the market do not have this feature. Anyway, if you want to get rid of the teardrop, there's 3 ways. One is very simple, that is recommended. I don't want to mention, but those will recognize who it is. You can do very slow, so you have very thin layer, and of course you since you have no lacquer, you don't see the drop. Then you can also have very fast, only one speed, very fast, so you have a big drop but at the bottom of the lens, there where the lens touches the lens holder. And then you have the smartest way, which is when you go to normal speed until half of the lens, because the segment does not go to beyond the half of the lens, and then you give acceleration to the maximum. So it's conjugates the gravity acceleration from the gravity and acceleration from the robot, and then this droplet is expelled out of the lens. That's it. But again, this feature is not offered with all robots.
Okay. So from this point of view, would you say that dip coating has some principal problems that spin coating not have? So would you recommend spin coating because you don't have the problem with the gravity?
Well, you still have when you do front side, it's okay. But when you do backside, it's okay. But when you do front side, it's different because you still have the curvature of the lens. That's one side. And also thing is the productivity of speed coating, because you need to do one side after the other, okay, and one lens after the other. Whereas with speed coating, you can have lots of lenses at the same time. Of course, the curing will be faster with spin coating, but that's where it is very different. Many people believe spin coating is a solution for small labs. Well, it is when you don't want to do AR, because the main difference between the lacquers that are used for spin coating and the ones that are used for dip coating is their chemical nature. All the lacquers for spin coating are UV curable. The ones for dip coating are thermally curable. In order to be UV curable, you need to be mostly organic. So it means the consequence It's really easy to get adhesion over the lens, which is organic, but not so easy to get adhesion with the AR, which is inorganic. On the contrary, with the thermal curable coating, which are mostly inorganic, it's quite difficult. That's why you need disactivation, chemical activation to get adhesion with the lens substrate, but easy to get adhesion with the AR coating that comes later because it's inorganic too. That's because you're recreating some kind of mineral glass surface at the top of the lens. On the other hand, and that's why I never wanted to push on UV curable coatings, think about one thing. In order to cure those type of lacquers, you need UV activation. UV activation creates free radicals. Free radicals, think about what is generating the cancers. The free radicals. I can tell you because I've seen that in the lab where I did my PhD, there were people working with those acrylates, and none of them did not develop a cancer. They all developed cancers to various stages. Some of them, they had very short pension times because they developed cancers, whether from their hands. At the time, they were not wearing masks. If you want to use a UV curable coating, if you don't want to develop cancer, you should always wear masks, gloves, protect yourself completely, which in practice never happens in a lab. So I don't want to kill my customers. I prefer them to have long life in front of them. That's why.
Oh yeah, I didn't know that.
No, nobody will tell you because
that's a very sad story.
Because well, you know, a lot of applications use UV curing because it's fast. But if you think about the free radicals, you know yourself, not being a chemist, but what the free radicals do with the cells.
Okay. Yeah, thank you. Thank you so much, François.
It was nice speaking with you, and I wish you a nice day, a nice weekend.
I also wish you a nice day and weekend, and have a good lunch.
Yes, thank you.